Okay, so there's going to be two parts to this talk. The first kind of half is going to be just about the algebraic approach to studying quantum spin systems, particularly to studying things in the thermodynamic limit. And this is going to appear in a bunch of other talks, or at least a couple other talks later this week. I know Dave and Yoshiko will be talking about things in this framework. So I thought I would introduce that and explain, why we do things in this with this algebraic approach, what you get out of it. And then the second part is going to be about quantum cellular automata, which are kind of naturally defined in this algebraic framework. So that's why I'm doing these two separate pieces. They're kind of disjoint, so maybe some people will like one and not the other. So good, then something for everyone. Okay, So what is the algebraic approach to spin systems? Well, we start with the lattice. And lattices can actually, for me, be anything. But here I want you to think something like ZD inside RD. Okay? And I'm just thinking of this as a metric space. You can actually use any discrete metric space you want to. It doesn't even have to be embedded in RD. But this discussion's easier if we're working with something more familiar. And then we have a local Hilbert space. H, which is going to be finite dimensional. That D is different from that D. Okay? And this is kind of the basic setup before you start, for a spin system. And in particular, for any finite L, for any finite subset F inside L, I can take the tensor product of this Hilbert space over the sites, and this is going to be the Hilbert space for the system on this little patch of lattice, right? This is the little Hilbert space here. And we have the operators localized here. Namely, it's the operators of all bounded linear operators. So I come from an operator algebra background, so I always use B of H to mean the algebra of all operators on this Hilbert space. If this were to be infinite dimensional, this would mean bounded operators. Here it's finite dimensional. So this is, of course, just a matrix algebra, right? Finite dimensional matrix algebra. But in particular, it's isomorphic to B of H to the tensor n, okay? And these are the, the observables and the unitaries and stuff that are localized on this patch of lattice. They live here. So what we're interested in is describing the thermodynamic limit. So thermodynamic limit, I'll call it just TDL, the thermodynamic limit. You want to see what happens when these patches increase to the whole infinite size of the lattice. And so naively, what you would like to try to do is to take, the infinite tensor product of these Hilbert spaces, and that would be your Hilbert space in the thermodynamic limit. But from a little bit of experience, you learn that this fails miserably. You can define a infinite tensor product by making a whole bunch of choices, but the physics you get really depends on the choices you make. And if you're trying to study this state and you make choices to get that state, they're not compatible. There's different, what you would say, super selection sectors in the thermodynamic limit. So this doesn't work. Doesn't really make sense. Okay? So what do you do? Well, you can actually make sense of the infinite tensor product of these algebras of operators. Okay? So if F is sitting inside G, so I have two little patches and one's included in the other, then I actually have this, let me call this algebra A sub F. It's the algebra assigned to this patch. We actually do have an inclusion of algebras, of associative algebras from AF into AG. Right? And what do? You just tensor with ones everywhere. So if I have a little patch, here's my, maybe it's, let me make it a lattice patch here. Dot, 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 dot. Maybe here's my F, and here's my bigger G. And I have some operator X that's localized here. Well, what I can do is just kind of stick ones. One sub h's on all these sites. And then I can think of this operator that was living in AF, now living in AG, with just sticking tensor ones in all the tensor factors. And that's an inclusion. This is an injective inclusion of algebras. And so what you can do is you can take the colimit, which, okay, if you think of these as literally sitting inside each other, it's just a fancy word for union. Over finite sets of these A sub F's, and that gives you an algebra we'll call A. So you can take this colimit in different categories. These are associative star algebras, so you could take the colimit in the category of associative star algebras. That's what you call the local algebra. If you think of these as C-star algebras, so they have norms and additional structures, you can take that limit, and this will be a C-star algebra. That's called the quasi-local algebra. For the purposes of today, it doesn't matter which one you take. Traditionally, people who work in this field usually take the C-star algebra, and there's reasons for that. But for what I'm talking about, you might as well just take not complete it, and you get what's called I'll call this the local algebra. And yeah, and so the idea now is if you want to talk about things like states and Hamiltonians and time evolution in the thermodynamic limit, you can do it all in terms of this algebra, right? So states are just positive functionals on A, normalized so that they're 1. And of course that, like, if you restrict this to any of the subalgebras, that will give you, your density matrix formulation. You can talk about Hamiltonians. They're just, I won't even write it down. Hamiltonians are just derivations on this algebra. And then time evolution, so what's the analog of a unitary? Usually we think of time evolution, or symmetries for that matter, as being unitaries on these Hilbert spaces. Here they're just going to be automorphisms of this star algebra. Okay, and so you can write down Schrodinger's equation where you have a one parameter automorphism group, and you can take the derivative at 0 and get a derivation, and the whole theory works. But you phrase it in terms of this algebra instead of a Hilbert space. So this is the algebraic perspective to doing spin systems. Any questions about that? Yes.
Yeah, you haven't invoked the Euclidean metric yet, and there are no Hamiltonians, so you don't need it yet.
Yeah, so the metric will come in if you want local Hamiltonians. And what do you mean for your Hamiltonian to be local?
So it really doesn't matter yet.
No, it doesn't matter yet.
But then that kind of means that ZD is the same for any D.
For any, no, because actually these algebras are not isomorphic. Oh, yeah,
It's
yes, for any D, yeah. It
It
changes with H, yeah, but yeah, for any D they're isomorphic at this point. Yeah, that's correct. Yep. Yeah, it will matter later, but right now it doesn't matter.
And they're all L2.
No, these algebras are not the algebra of all bounded operators on a Hilbert space, and that's the whole point. These are interesting algebras. They're called, if you complete them, they're called AF C-star algebras, and in particular, they're UHF C-star algebras. But they're highly, they're not trivial. They're not just all the operators on some Hilbert space, and that's the point. These are just the local operators in your system, and that's why you can have things like different phases in the first place, different superselection sectors, inequivalent representations of this algebra on Hilbert space. And that's like part of the reason why spin systems are interesting in the first place. Why you get phases is partially explained by the fact that this algebra is not all the operators on a Hilbert space.
Quick question.
Yeah.
I didn't understand this adjective positive.
Yeah, sorry. So I think I'm doing these boards wrong because I feel like I'm not supposed to be like crouching. Does anyone have a suggestion?
Yeah,
Thank you.
All the way down.
I always struggle with board dynamics. If you see me, there's actually several recordings of me giving talks with fancy boards like this, and it's every time I have a bit of a struggle. So it means this. Okay. So just for any operator in this big infinite dimensional algebra, phi of x star x is greater than or equal to 0. And the state condition, you also want phi of 1 is 1. That's the normalization condition.
So phi you think of as your state?
Phi is the state. Yeah, and you should think about it, in the finite dimensional case, it's like taking trace against a density matrix. That's the functional you get from your density matrix form. Yeah.
Does this limit depend on the topology of your lattice?
It doesn't. So it just, it just depends on this poset of finite subsets, and that only depends on the structure of L as a set. And so any countable set, you'll get the same thing here. So it doesn't depend right now, but stuff will come in later. Like when you talk about local, we haven't started doing physics yet, right? I guess you could say, with states and stuff like that, but the key point is that you want to do local physics, and there your Hamiltonians and things are going to have to depend, they'll be local, and that will depend on the metric on the lattice, yeah.
Second question, how explicit can you calculate these algebras? Because these are limits over.
Yeah, so people who do operator algebras understand these very well. So I would say very well. Like the whole topic of operator algebras is literally like study these infinite dimensional algebras. And these are like the first interesting examples in some sense of of C-star algebras, at least when you complete them. I only care about the dense subalgebra. We understand them very well, yes.
Is the category of C-star algebras closed under colimits?
Yes. That is a first theorem.
Okay.
Yes, that is a fact. Yes.
But for calculations, you don't need really the limit. I mean,
Well, it depends on what you're trying to do. So if you take a derivation and you want to integrate it to get a continuous time evolution, that will often involve some kind of norm because you need things to converge, and there you really want to be talking about the C-star algebra. But what I'm going to do with quantum cellular automata doesn't actually, we're talking about Hamiltonians, and here I just need this finite algebra. But actually in practice, for most calculations, you're right. Even when there is a convergence thing, you still look at the finite dimensional pieces at a time. There's just infinitely many of them, so you can't, you have to kind of consider them all at the same time. Yeah. Yes?
Point of discussion, does it make difference in terms of automorphisms if the unitary is a evolution under a given local Hamiltonian or just some completely general unitary?
At this point, I mean, if we wanted something to be counted as a time evolution, we would want ones that come from Hamiltonians, but that's kind of the point of quantum cellular automata, is they're a different way of doing it. But at this point, yeah, just any automorphism would count. But we haven't gotten enough structure to talk about that yet.
But are those some special automorphisms?
Yes, those are very special. Yeah, those are those ones are very special. A generic automorphism would not be counted as physical. And
Do you have a group structure? Or?
yeah, it is a group. Automorphism is still a group. It's just like most of them aren't good for doing, like, for example, as was pointed out, these algebras for different values of D are all isomorphic. And so things that were good for working with ZD probably shouldn't be good for working with ZD plus 1. Like the physics doesn't match up. So, but they're all equally good automorphisms. So, yeah. Okay, this is great. I love questions. Okay, anything else? No? Okay, good. So what we're going to do immediately is notice that you can generalize this. This is a kind of a classic mathematician thing to do, is to take some really natural physics thing, be like, oh, look, I can just abstract it away and generalize it and then go study those things. So that's what it's going to look like at first pass, is that's what I'm doing. But I want to motivate these things a little bit. So let me define an abstract spin system. Is a star algebra, and again, maybe you know, C-star algebra. So if you don't know what that means, don't worry about it. It's just think about associative star algebras, A, and an assignment for every finite subset of L, we're going to get a finite dimensional subalgebra of A. Okay, such that the following things hold. If F is contained in G, then I should have AF sits inside AG. 2, so this one is important. If F and G are disjoint finite subsets, then the two algebras should commute with each other. And so that certainly happens over here, though we didn't point it out, because if F and G are disjoint, right, the operators localized in F have 1s in all the G slots, and the operators localized in G have 1s in all the F slots. So clearly they're going to commute with each other. And then 3, you want to make sure that the algebra A is the union, or is generated by all the AFs. F subset L finite. Okay. So that's it. Yes.
2 things. One, your shoelace.
Yeah, I noticed that. Thank you. Yeah.
And the other one is, do you mean unital subalgebras?
Yes. Yeah.
I'm guessing later there'll be some that are not unital.
No, everything's going to be unital for us today.
So it's not, because there's a Morita thing with an idempotent projection, right? Idempotent subalgebras.
Yes.
Or you said finite out loud, but you didn't write finite for the.
Finite dimensional.
Oh, you put it over there. Okay.
FD stands for finite dimensional. You mean finite subset?
No, I thought you would put it over by the F inside of L.
All our Fs and stuff are finite subsets. Yeah. Okay. Same kind of framework. Okay. So what you're supposed to think of this algebra A as being is exactly like this algebra over here. It's the algebra of all local operators, but taken together. And these A sub Fs, you're meant to think of as the operators that are localized in the region F. Namely, like, if there are observables here, then the outcome of doing your measurement of that observable isn't going to depend on how the system's changing outside F. Okay, that's how these AFs are supposed to be. This is kind of a locality condition, right? If I do measurements in faraway places, or at least disjoint places, they shouldn't have quantum, non-commutativity going on. And then this just says we didn't throw in operators that weren't built out of the local operators. Okay. And again, if this was a C-star algebra, if we were working in the analytic framework, I might complete this in norm and say that something like that. Like this algebra generated by these is dense or something. Okay. Yes.
Why did you use colimit there and just union there? I mean,
Because yeah. So here I didn't have A. I had to build A. And now that I've built A, I can take the image of AF in the colimit.
Defineness is equal to. It's not defineness. It's saying that this should be the union of those.
Yeah, it's because So it's a funny thing. It's a definitional thing. Here I started with the AFs independently, and I had to build a big algebra out of them. Here I'm just saying, suppose the definition is I have the big algebra, and then these things are sitting as subalgebras. So that's why. It's because here I had to actually build the A, and here I'm just assuming that I have one. But of course, in practice, you're going to build the A's exactly like this. You're going to define, when I define an example of this, I'm going to take a colimit of algebras like this.
And also, I've heard before that when you deal with many boards, it's better to start from the board behind.
Yeah.
So it may be
That makes sense. So that you can see. So
you can cover it, and then you can lift and show people the old work.
Yeah, I
And
agree.
I guess my mind's still trying to wrap around the functional idea. Like, I mean, you said think of it a trace.
Yeah. So okay. So in the usual, so if my algebra is all the operators on a Hilbert space, then there's this theorem that says positive linear functionals. Or I'll just call them states because that's what we call them in operator algebras. But they're positive linear functionals normalized this way, are in bijective correspondence with density matrices. And how does it work? Well, how do I take a density matrix and build a positive linear functional? Well, you just take, if rho is a density matrix, you consider the functional, which takes trace against the density matrix. So if I have an operator, I multiply the operator by rho and I take the trace. And that will be a positive functional satisfying these conditions. Conversely, in this case, every positive linear functional is uniquely represented by a density matrix in this way. Okay, so that's kind of the correspondence. And of course, in the infinite case, or in this case of A, you don't have an analog of density matrix, really. You kind of do. I won't go into it, but yeah. It's easier just to talk about it as a positive function. Yes?
To paraphrase what you're saying as a physicist, can I say that on the left side you're starting with states, and on the right side you're starting with operators? Is it how you're
Yes,
thinking
yeah,
of it?
exactly. Here you're starting with this, and then you notice to go to the thermodynamic limit, it's convenient to pass to the operators and talk about the infinite tensor product of operators and do physics there. So now we're just going to start with the operators, and here there might not be local Hilbert spaces. Okay, that's the whole point, is that there might not be a little thing. In particular, these algebras they're not just matrix algebras. They're multi-matrix algebras, so they're always, the AF are always direct sums of matrix algebras. But you can have these local selection sectors. Okay, so they're finite dimensional star algebras, and I guess I should probably, with the C star condition at least, these will be, these kind of algebras here. So they're multi-matrix algebras, but they're not necessarily all the operators on some local Hilbert space, because there's no center in those algebras. Yeah, we have local kind of selection sectors in some sense.
So it's a generalization.
It's a generalization, and I'll show you why we care about these. Yeah.
So if my system exists on some space with non-trivial topology, and I can have string operators that wrap around the whole system, can
Yeah.
you describe those in this language?
Yeah, absolutely.
But these are just local algebra. There's algebra of local operators in some patch.
Yes.
So how can you describe
But you take the whole patch as you for the whole system, and string operators then are not represented as elements in this algebra, but as quantum operations that you can do on this algebra. So like quantum channels, you represent the string operators as channels. So you don't think of them, in finite dimensions, you might as well just think of them as operators from Steinspring dilation or whatever. But in the infinite case, yeah, the way you think of string operators is either as quantum channels or as, endomorphisms or whatever, super selection sectors if you're, well, not super selection sectors, but yeah, endomorphisms or quantum channels on the algebra. But my claim is that everything that you do, if it makes good sense, can be done in this framework. And things that don't make good sense, it means you have to think hard about the definition even on the physics side.
By quantum channel, do you mean something that acts on the functional?
Okay, yeah, so no, a quantum channel for me is going to be it's what's called a unital completely positive map between algebras. I won't go into that right now, but it does act on the functionals.
TPCP.
Well, the dual of that. So a unital completely positive map is actually dual to a completely positive trace preserving map. But yes, the same information. Okay. Oh yeah, right. I'm supposed to do it this way. Okay, so why would we care about something like this? If we're true physicists who always have our Hilbert spaces, why do we care about something like this? And the first most obvious reason you would care about something like this is if you have symmetry on your system. So suppose I have one of these, and I have a group or a Hopf algebra or a weak Hopf algebra or something acting on each local Hilbert space. And I care about the operators that are invariant under that symmetry. Okay, so if G is acting on my local Hilbert space H, so I'm over in this situation, then I can take the fixed points, the local operators that commute with the symmetry. And this will assemble into a net of algebras just like this, but it is no longer the case that the algebras factorize as a tensor product of the local pieces, right? This is exactly like if it's literally just the fact that if I take a tensor product of group representations, the intertwiners don't factorize as a tensor product of the intertwiners of the individual pieces. So if you care about the symmetric local operators or the invariant local operators, you're forced into this situation to care about these. So there's a symmetric local operators. Our abstract. And of course, our abstract spin system. And this will make sense for whatever kind of symmetry. It's easiest to picture with group because we're all familiar with that. But if you have a Hopf algebra symmetry or a weak Hopf algebra symmetry or a categorical symmetry like an MPO symmetry, so this will work for weak Hopf MPO / whatever you mean by categorical symmetry. Any kind of notion of symmetry, there should be a notion of invariant local operator. Whatever you define for your symmetry, that should make sense. And probably those invariant local operators will form one of these abstract things. And so if you want to do physics that's invariant under your symmetry, you can do states and dynamics and stuff on this algebra of symmetric operators. And that's one way to make sense of the thermodynamic limit, the symmetric thermodynamic limit. Okay? And in fact, one way to interpret, Mason mentioned that everyone means something slightly different when they use the word gauging. One thing you could mean by gauging something that's happening over here is translating to something happening over here on this algebra of invariant local operators. That's one thing you can mean by that. Not everyone means that, but that is certainly one interpretation.
I just have a question. Maybe
Yeah, sure.
If you're interested in symmetric systems,
Yes.
you still need to look at operators that are not invariant under the symmetry.
Yeah.
Because you want to that's an important probe into the system.
Yeah, but this is yeah. Sure. True. Okay. So that's one way. That's one place these things come from. But there's another place where these come from that actually Dave is going to talk about in detail. So I wanted to mention it a little bit because it provides some motivation for the QCA stuff. But actually, Dave Pennies will actually go into detail about this. So this is one kind of motivation. Another is these things arise as the boundaries of local topological order. So boundary algebra. So I mean boundary slightly different than people who usually say that word means. So boundary algebra of local topological order. So what is that? So first of all, by local topological order, I mean I'm in this setting of the the commuting projector system, exactly solvable model. Think things like toric code or 11 WEM models. I have these local ground state projections. Okay, and one of the reasons we care about those is those are error correcting. Start with the backboard.
Yeah, but underneath there's like one bit. That's not either.
Oh, you mean this?
Yeah, you can start with that if you want.
What do you think? Let's take a vote. Who thinks I should do this one first? No one? Okay, I'll do this one first. Okay. That's pretty clear. So I'm in this setting of local topological order. So I have these local ground state projections that are error correcting. So what does that even mean? So for any patch F, I have this projection P sub F, which is local ground state projection. And for these, what we mean when we say these are error correcting against local errors is that for any x in maybe, so I'm going to consider some, here's f and here's f prime, that's kind of in the interior of f. So for any operator localized in AF prime, when I squish it between these ground state projections, I get some scalar times the ground state projection. Okay, so if I go far enough into the middle of my local ground state projection and I squeeze it between, I just get a scalar. So this is the special property that defines local topological order. This is what we mean by local topological order, is a bunch of projections satisfying this condition. They usually arise as ground state projections of some commuting projector Hamiltonian. Okay, well, what if you take errors near the boundary? So suppose I have this f, and I do some operator that's actually sitting on the boundary. And I try to do the same thing, and it doesn't collapse into a scalar because, you know, I needed it to be far away from the boundary. But it does kind of stabilize and assemble into a net of operators in one dimension lower. So I'm imagining I'm cutting this 2D system. I now have this 1D lattice, and I look at my operators that are localized near the boundary, and I squish them between this. So I'll define, you know, if this is some interval I, I'll define, you know, A sub f, or maybe B sub f, it's a new net now, to be the operators localized in some little region near the boundary in A, and then I sandwich them between these things. So B sub I is something like, so I'll just, you know, do an impressionistic picture. Dave will give you a better formal definition, but it's like PF X, it's like PF A sub, it gets too complicated, boundary of F, PF or something like that. So this is not just scalars times PF. There's non-trivial things that survive. They don't collapse away, but they give me an algebra. And if I think of that algebra as being assigned to an interval, which I've made by cutting the boundary, then these actually assemble into one of these things. And we call this a boundary net of algebras. It's a way of talking about, one way to think about it is that you can assemble the error. If you cut a boundary, you can assemble the errors compressed by your topological ground state projections into one of these things. And it turns out that you can actually understand the bulk system purely in terms of studying this net. And so Dave will talk about that on Wednesday. But for example, this net will recover the topological order of the bulk and all these sort of things just as a pure algebraic object without even picking states or Hamiltonians on this net of algebras.
It feels like this is the moment where you turned on the metric.
Yeah. So here you definitely need a metric. Yeah, you need to cut and you get codimensions and things like that. Yeah.
You have some Hamiltonian around if you're talking about ground state.
Yeah, right. These things have to be local.
It doesn't necessarily have to be constructed using a metric. But this bit does. That word boundary implies there's a metric.
Yeah, that's exactly right. Yeah, it's boundary. Yeah.
But the projection on the boundary, you have different choices. Like there might be a unique projection for the bulk.
No, it's not a boundary theory. That's the thing. I'm just literally cutting my system along a line. I'm not actually putting some extra degrees of freedom on boundary. I'm not changing my state or my projection. So it's like, you know, if I'm on a lattice, I'm literally just taking the Hilbert, like tensor product of Hilbert spaces assigned to the points and just applying the terms of the projections that live inside and not applying these on the outside. And so that means when I compress this, I get all these errors. They don't go away. So I don't have a gapped boundary here. There's no boundary theory. I'm just kind of, that's why, you know, maybe this choice of word boundary algebra is misleading. Because every physicist, when you say that, thinks, oh, what's your boundary? You have a gapped boundary.
Restricting the projection to just this.
Yes, exactly. And we're creating an algebra that captures the error. Now, any boundary theory can be described as like a state or something on these algebras. Like boundary states and all that stuff makes sense as states on these boundary algebras. Okay, so this is one way to talk about boundaries kind of in a more mathematical algebraic sort of way. You can talk about the different boundaries as states on the same algebra here. Okay, but these sort of things kind of live independently. And this will be the focus of Dave's talk. I don't want to say too much more, but there's this nice kind of boundary net of algebras that appears and seems to be really interesting and important. And you can rigorously study a lot of the things you normally do for bulk topological orders. You can do it with the boundary algebra in a nice way. Okay, so that's all I'll say about that for now. Yeah.
Is PF just an element of B?
Yes.
Algebra? Yeah.
Well, this is now, you know, in an ordinary spin system, it's a local ground state projection that acts on the the tensor product of the Hilbert spaces. So now we're in, this is, you start with a concrete thing, right? This is an actual tensor product of Hilbert spaces, Hamiltonian, but then you produce this abstract thing by compressing along the boundary of these PFs. And now you're in this situation, and I'll actually tell you, you can identify these for like toric code and 11-Wen model, and I'll tell you what they look like by giving you a nice class of examples.
Can you explain this definition of A sub partial F?
Yeah, so it's a little bit loose here, but you just take the operators that, I'll just define this to be partial F as some strip along the boundary, and then you prove it doesn't depend on how you pick that strip. Okay, so you make some choice, like if here's F, I chose a boundary, like a big global boundary by cutting my system, and then the boundary of F is just where F intersects that. You just pick a little strip around that, and that's what I'm calling delta F.
The width of that strip might matter in practice.
But we prove it doesn't. So for local topological orders that satisfy this, and actually we put an additional condition that basically says that the width of the strip doesn't matter. Basically, it's a stabilization condition. Dave will get into details. But for things like 11-Wen model and toric code and stuff, we prove it doesn't matter.
Can it be with
That's because
zero,
that's a
though?
zero correlation length.
The width of this strip can be 0. No, yeah.
11-Wen models have zero correlation length. That's why the width doesn't matter.
Yes.
For general models, there's some finite.
Yeah,
correlation.
exactly. Like this is not.
Matters a little bit.
Yeah. That's right.
It just has to be big enough.
It has to be big enough. That's the thing. A lot of this stuff is like a big enough sort of thing. Yeah. The width doesn't matter as long as it's big enough.
So an 11-Wen model, you're saying the width could be 0 then?
For 11-Wen model, yes, and that's a very special case though. For toric code, it can't be, or quantum double models, it can't be.
You know, quantum double models, it's like 2 or 3. And
Yeah. So we've analyzed this in all the standard commuting projector models.
In the case where there's a finite correlation length, you do run into the problem that big enough, there's always exponentially small corrections.
Tails, yeah, we don't deal with tails. Yeah, that's a big problem. So this really only is special to like this error correcting code world. Like this is special, Mason was saying there's 2 worlds. This is definitely specialized to the world of codes and is not stable against perturbation. At least we haven't thought about how to make it stable against perturbation.
You mean the definition of the boundary algebra?
Even having the boundary algebra, you need these local ground state projections. I mean, if you have a Hamiltonian that has these nice local ground state projections, if you perturb it, you lose the nice local ground state projection already. Like there's already tails and stuff. So you need that, and that's not stable already under perturbation. But yeah, so more questions about that. Dave's giving a whole talk on that on Wednesday. So.
What F prime was,
It's just some sufficiently small f, like which would depends on the details of your system, how small it has to be. But it's like not that much smaller. It's like you pick some r and it's like within r of, it's like, the r inside shell or something. And it's a global r. Like it doesn't change as the f gets bigger. Okay. So let me give you an example of these abstract nets, and that's actually the main focus of my talk. These are called what I call fusion spin chains. And, I didn't invent these things. They've been around for a long time. But I think no one gave them an explicit name, at least as far as I can tell. So let's let C be a fusion category. And X is an object in C. We want it to be what I call a strong tensor generator. Which means that it's an object so that, just to be a tensor generator means that all simple objects in C will appear as some summand of a tensor power of X. But strong tensor generator means there's a fixed number where all the simple objects appear at some point. So it's a bit stronger. You can be a tensor generator and not a strong tensor generator. For example, if you take G-graded vector spaces, or like Zn-graded vector spaces, and you take the generator for Z, that's a tensor generator, but not a strong tensor generator, right? Because everything appears as a summand of some power, but I can't get all the group elements appearing at the same time. And you have this problem anytime you have a G grading on your fusion category. If you pick a generator that's not in the trivial component, or at least is homogeneously not in the trivial component, you run into trouble.
You take X just to be the direct sum of all.
Yeah, so for example, you always have these. You could take X to be the direct sum. Yeah. But this is a parameter in the construction of the net. Yeah, but there always exist these things.
Can you give an example just so?
Yeah, so Eric's example is really good. Set X to be the direct sum over all simple objects. So that will certainly, I can pick, this is a strong tensor generator because all objects appear in the first tensor power of this thing, right? All the simple objects appear as a summand. A little bit of a less trivial example, take C as rep S3, and take the irreducible representation, the 2-dimensional irreducible rep. Rho is 2-dim irrep. Then if I take, so this is a simple object, but if I take rho squared, it's the sum of all three irreducible representations, right? It's like trivial plus sine plus rho. And so this would be an example of a strong tensor generator.
Okay, so any Tambara Yamagami one then.
So no, so in Tambara Yamagami it doesn't quite work, because if I take that graded component and I square it, I get all the things except for itself.
Okay.
Yeah. So and then if I square it again, I only get the row, copies of row. So I can't get the G's and the row at the same time with just row. So I would have to do something like take row plus one of the group elements, or I wouldn't be able to just use the Tambara Yamagami.
Yeah. Good.
Okay, so it's kind of a technical requirement, but you need it for this net of algebras to kind of see the whole category. Otherwise, you're doing something funny and you miss a piece of it. So let me just use the same board. So here's an example. Okay, so we're going to build a 1D net out of this. So I didn't tell you, we're going to build an abstract spin system. Build a 1D abstract spin system. And here's how. So since it's 1D, I'm just going to tell you the algebras that I assign to an interval. And then for any more complicated region that's a union of disjoint intervals, you're just going to take algebras generated by the two different intervals inside a bigger thing. So if I have I, with the number, so when I say this, I mean the number of points in I. Okay, I is an interval, but I'm going to take the number of points since we're discrete. Then I'm going to define the algebra A sub I to be equal to the endomorphisms in my fusion category of tensor powers of this special object we picked, x to itself n times. So if you like pictures, right, I'm just taking these pictures. I have n things here. Oh, look, the n match. Great. So it's just the things I can draw with this, and the strings are all labeled by the same object x. Okay? So this is the algebra I'm going to assign to an interval. And then there's natural ways to include these into each other by tensoring with identity strands in the fusion category. No, I'm going over here. Okay. So if I is a subset of J, then I have a natural inclusion AI into AJ, which just works like this. I take my, here's my I, and here's my J, my bigger J. I'm just going to stick the strings on, however many I need. Okay, so something quite simple. Pop it. And I guess I'm assuming my fusion category is strict or whatever, just to make this easier to not have to talk about associators and stuff.
Unit objects?
What's that?
What do you put on the vertical strands?
They're all strands are labeled X here, where it's the generator we chose in the beginning. Yes.
So you're not assuming that the objects are in some way ordered, or like here, for example, how do you know that the I inputs are next to each other, or you just?
I am only defining it for intervals right now.
Oh.
Yeah. No, I need that. Yeah. It has to be intervals. Okay. And then you define the big A to be the colimit over intervals. Of these A sub i's. And that gives you a big algebra. And now I can define for a more complicated region that's not a product of intervals. This big algebra will have subalgebras corresponding to those intervals, and I just take the algebra generated by those two things. So you kind of define it using the intervals, and then for disjoint regions, you just take the algebra inside here generated by those two intervals. Okay, so here's your big algebra. And the local algebras, AI, are kind of sitting inside here naturally, and those are going to be your local algebras. Okay, and they'll satisfy all these axioms very easily. Like the commuting of disjoint intervals is just this fact in tensor categories that this equals this, which of course is exactly the thing that's generalized in parafermions that Arthur was talking about. But in tensor categories, you just have this sort of thing. That's this condition. Okay. Any questions about that? So these are what I call fusion spin chains. Because they're 1D, so I feel like I can get away saying fusion spin chain. Okay, and if you take these examples, so if you do this with toric code, you exactly get a fusion spin chain for vec Z2 or Z2 graded Hilbert spaces where your object is the sum of the simple objects. So it's this one. And that's what you get in toric code. For quantum double models, Dave, is it the sum of the simple objects, or what you for quantum double non-abelian quantum double models?
That's what we use.
Yeah, you get the sum of simple objects in the generator, and then also in Levin-Wen models, you also get this one. So in all the cases where, like in this boundary algebra setting,
Double, you get either the group algebra or continuous functions.
yeah, you get something, but yeah, and then in Levin-Wen model, you get this one. When you build the Levin-Wen model out of a fusion category C, the boundary algebra is a fusion spin chain, where the generator X is the sum over the simple objects. Okay.
For like a Hopf algebra, you just take H itself.
Yeah, or you actually for Hopf algebra, if you have it acting on the Hilbert space, it's literally that object as an object of the Hilbert space, or as the object of the category. It is a representation of a Hopf algebra. So you use that object in the category.
It's always tensor product.
It's always tensor product.
But for these anion chains, I thought they're not.
Yeah, so if it's a weak Hopf algebra, you have to do something a little bit funny when you define invariant operator. How do you take the tensor product of two Hopf algebra representations? You don't take the tensor product of Hilbert spaces. You have to quotient out or project onto a subspace using the separability idempotent. And so you have to use that restricted tensor product, and then you take local operators on that restricted tensor product that commute with the symmetry. So yeah, for weak Hopf algebras and MPOs, it's slightly different how you define invariant operators in the first place. But it is still the invariant operators. You just have to, they're supported on this, like you said, the chain where all the labels have to match. So you take operators where the labels have to match that commute with the symmetry. But for Hopf algebra specifically, it is just tensor product. In group algebras, it's just tensor product.
In Hopf algebras, you take the the operators that commute with the Hopf algebra, so it's really
the intertwining.
Exactly, it's the intertwining operator. So
it's just the intertwining endomorphisms of the tensor product representation. Yeah. And weak Hopf algebras, it's the same. But when you just try to do it as a physical Hilbert space, it looks a little weird. It's not the tensor product of Hilbert spaces. It's still, that's all I'm saying. Yeah. Weak Hopf algebras are weird from that point of view. And the same thing happens if you want to do like matrix product operator or categorical symmetry. It's the same thing as weak Hopf algebras. Yes?
Is there a relation between different choices for strong generators?
Yeah, so that's a great question. So I don't have a full answer to that question. They're not always the same. I know they're not always the same. I can pick two strong generators for rep S3 that give me algebras that are, the big algebras are just not even isomorphic as algebras. So yeah, it does depend on your choice. But there should be some stabilization you can do that makes that choice irrelevant. But yeah, yes.
I didn't quite get why this thing needs to be strong.
I haven't told you why. A priori, none of these constructions, you can do them all for any, it doesn't even have to be a tensor generator, just as pick any object. Okay, but the thing that I'm calling a fusion spin chain, I'm going to want it to be tensor categorical. Okay, good. Any questions about these things? So I think I'm ready to talk about quantum cellular automata now. Oh no, not yet. So what's the difference between one of these things and an ordinary spin system? Well, these things don't factorize locally as tensor products of matrix algebras. They don't factorize as the on-site things. And so there's some kind of like topological stuff going on locally. These things are kind of bound to each other, almost a sort of algebraic entanglement. Because in particular, if I take the algebra assigned to an interval and I partition it as subintervals, it's not generated by the two subalgebras. There could be new operators that appear that weren't there before. So there's a kind of algebraic entanglement. How do we capture that? And so one thing we can do is introduce what I call, I guess this is the board I want, a kind of super selection sector, but not of states. So this is going to be a little weird. These are called DHR bimodules. Let me try to explain what's going on here.
So Corey, are you saying that the 1D abstract spin system you define there doesn't satisfy the axioms that you wrote?
No, it does satisfy the axioms, but the tensor product axiom. Like, it's not true that, so if I take I and write it as K union J, like maybe I partition I into K and J, it's not true that AI is not necessarily generated by AK and AJ. There could be an operator in this interval that wasn't a product built out of products of operators in these intervals.
You wrote that equation. A is.
But the whole algebra is generated by the local ones, so certainly AI is good enough. Like I can't just pick a finite set of interval lengths. Now actually you can. It is true in most of these examples that if I take all the intervals of length k, they generate the whole algebra, but they'll need to be overlapping. So these are disjoint things. Maybe I didn't make it. Yeah, because we're discrete. So yeah, so there's a kind of algebraic entanglement going on here in a sense. So here's the theorem, I guess I'll say, is that associated to any abstract spin system, satisfying a condition that I'll call a weak algebraic Hogg duality. Weak, it's just a technical condition which all these fusion categorical nets satisfy. Weak algebraic Hogg duality. Satisfying. There exists a braided tensor category. I'll call it DHR of A. And it's the category of DHR by modules. So I'll tell you what these are in a second. But the point is, associated to one of these abstract spin systems, in particular these sort of things, there is a braided tensor category without picking a state, without picking a Hamiltonian, just the net of algebras itself. Okay? And so if you're thinking about these as coming from boundary algebras, what's happening is that you're passing the interesting kind of entanglement properties of the projections purely into the algebraic entanglement of the boundary algebra in a way that actually recovers the topological order, because the next theorem I'm about to write down is for fusion category spin chains. This DHR category is the Drinfeld center.
Is it finite dimensional or infinite?
The algebras are infinite dimensional.
Is the sentence complete there?
Probably not. Associated to abstract spin syst A, it has to satisfy a property. There exists, or there is a braided tensor cat called DHRA.
I'm used to a Hogg duality for Feynman algebra.
Yeah. So this is an algebraic Hogg duality. I'll write it down for you in a second. Yeah. This is related to that, but it's way weaker. Yeah. Much easier to satisfy this than actual Hogg duality. Yeah.
Just to clarify this theorem, you're not depending on dimension, right?
It does. Well, yeah. So how you actually build the thing does depend on dimension.
So it's not any abstract spin system.
It's any abstract spin system, yes, but it depends on the lattice. Like the abstract spin system comes with a lattice as part of its data.
Is there some assumption of a gap or something?
No, there's no state, there's no Hamiltonian or anything. It's just these algebras. And the point is that, like, if you're thinking of these as coming from the boundary of a topological order, the bulk had all that stuff going on with the local projections, but you use that and you pass it to just this algebraic thing. And the claim, first of all, my claim is that this is capturing the algebraic entanglement. It characterizes kind of the order of algebraic entanglement. And what is happening in this boundary algebra story is you're passing the bulk, actual entanglement of the ground state, long-range entanglement of the ground state, to this kind of algebraic entanglement of the thing in a way that remembers the topological order.
Sure, but this statement alone could apply to like a gapless spin system as well.
So this statement alone is just about algebras, and there's no state. So when you say gapless spin system, that's not the kind of thing that's not an abstract spin system. An abstract spin system is just a net of algebras.
Is the point that if it weren't a gap state, I wouldn't be able to do that?
Yeah, exactly. Yeah, if the bulk wasn't a gap state, I wouldn't. I mean, this has all these nice ground state projections. The local commuting projector, I didn't tell you all the axioms that go into this. Dave will tell you that. But part of it is that when it's coming from ground states of a Hamiltonian, that thing's going to be commuting projector, so it's going to be gapped.
It's gapless, you fell there.
Yeah. In gapless, you can't even do this in the first place.
The commuting fails. The projector.
Yes.
Still harping. Your spin systems are on a lattice in Z.
Gapless state can still be.
You're
So
going to build this DHR algebra.
Yes. Or DHR tensor category.
By cutting it in half somehow.
Oh, no. Let me tell you how it works.
Because they're assuming commuting projector.
When A is this a fusion categorical net, let me call this thing, let me give it a name. Let me call this like A, C, X. It depends on a fusion category and a generator. And then I'll just say DHR of A, C, X is equivalent to the Drinfeld center as a braided tensor category. So that's where you need strong tensor generator. This theorem's not true if you don't put that strong tensor generator. Yes?
And
that's for that choice of the sum of irreducibles, or
For any x that's a strong tensor generator. It just has to be a strong tensor generator. That's the only condition. Okay, so for any net of algebras, there's this thing. Now, if I choose like the ordinary net of algebras that we started with, the concrete spin system, this of course is trivial. Right? So you only see this when you have this weird kind of algebraic entanglement where the algebras associated to an interval are not generated by these disjoint subinterval algebras. Okay, and this is, you can kind of think of this as a bulk boundary correspondence, although, at least in the boundary algebra case, when you're thinking about these things as coming from boundary algebras, but not really, because we're not talking about a boundary theory. We're not talking about like a gap theory on the boundary. We're just talking about like some kind of weird boundary algebra thing we're doing. So I would hesitate to call it bulk boundary correspondence, more that you can use these kind of boundary algebras to characterize the bulk topological order is our proposal. And in fact, you could even try to define the bulk topological order in the thermodynamic limit this way, if you wanted to. But anyway, okay, so that's the first theorem.
At some point, you stepped away from your one-dimensional restriction.
No. Yeah, okay, yes. So this is actually true in any dimension. Like the DHR exists and is braided in any dimension. But the theorem where I can
the setup to us over there, you were still using this.
So this is an example of an abstract one. This is now completely abstract, but for these particular examples, then you have this identification. Yes.
But in higher dimensions, shouldn't it be some higher tensor?
Yeah, well, so you get the symmetric tensor category of point excitations when you use this definition. There should be a higher tensor category, and that's what I was telling you about at dinner. Now it all makes sense. Okay. Yes. Oh, it's this net of algebras we built from a fusion category and a generator.
Like building the spin system.
Yeah, we built these spin systems. It took two pieces of data, a fusion category, and then a special object in that fusion category that tensor generated. And the net actually didn't need to be, this didn't have to be a tensor generator to build the net, but for this theorem to be true, we need the net.
So when you build it, you can imagine 2 dimensions sticking things in front of it too, like the.
Yeah, right. So if you had a braided fusion category, so this was just for fusion categories. If you have a braided fusion category, you can exactly build a 2D net, and that's going to be the boundary algebra for Walker-Wong model.
And where's the bulk boundary correspondence? Like, how would you see that as?
So in 2 dimensions, it's harder because you need a braided fusion 2 category, not just a braided fusion category. So we're working on that, but it's not done yet.
You mean that equation at the end there is?
No, I mean this is just for fusion categories, not for braided fusion categories. What's DHR of a Walker, like a 2D fusion category net? If you just apply this definition of DHR, you'll get the symmetric center of the braided fusion category, the Muger center, which of course is missing most of the topological order. You want the braided fusion 2 category, but this definition is just a regular braided tensor category, so it's missing the higher structure.
What I'm trying to say is that if this was a boundary thing, the A characterizes a boundary.
Yeah.
And then C, does the C correspond to your bulk? I mean,
Yeah, C is the braided category of the bulk you used to build the Walker-Wong model. Yeah. That's right. Yes.
So what you're saying here is that, so you said the ACX depends on the choice of X.
Yes.
But then you take the DHR and you get the same thing.
Yes.
Can you say anything in the more general theorem about, like when abstract spin systems give you the same DHR?
Yeah, I don't know. That's a great question. I'm thinking about those things, and I don't have a clear answer yet. No. So I want to tell you what this DHR category is. How do you define it? Okay. And I want to motivate this a little bit. I do still hope to get to. What time did I start talking? 45. Oh, and that's 5 minutes behind. Okay. Wow. Yeah, I haven't even gotten to quantum cellular automata yet. Okay, well, let's change. I apologize for all of you who are interested in hearing about quantum cellular automata. Let's just jettison that whole half of the talk and keep talking about this, because I think this is interesting and it's a good setup for Dave's talk on Wednesday. So for those of you who want to hear about quantum cellular automata, the point is that I'm studying quantum cellular automata specifically on these fusion spin chains and trying to classify them up to finite depth circuits and stuff like that. And that was part 2 of the talk. So if you want to talk about that, I'm happy to. But yeah, I'll just keep going with this for now. So let's define these DHR bimodules. Okay, so here's the motivation. We have this relation between states and Hilbert spaces, right? associated to a state usually is a vector, at least a pure state in this Hilbert space. But a Hilbert state is a whole bunch of states that are related to each other. Well, there's an analogy here. It's not a one-way arrow. It's just a wiggly arrow. If I have a quantum channel, this is analogous to a bimodule between algebras. So if a channel goes from A to B, this is analogous to an AB bimodule. And of course, if you can think of a state as a channel from A to the complex numbers, and then a Hilbert space, of course, is an A C bimodule, because A is acting as the local operators on this Hilbert space. So that's kind of the analogy. If you think of a quantum channel as a generalization of state, then the right way to generalize Hilbert space is by using a bimodule, or more appropriately, a correspondence between the quasi-local algebras A and B. So that's why we're talking about bimodules. They're kind of the analog. Bimodules are to quantum channels as Hilbert spaces are to states. This is like your SAT analogy, like they give you an analogy and they say which one is most like it. I don't know if you all took the SAT,
You're
but
dating yourself. They got rid of them about 10 years ago.
they got rid of them. Okay, wow. Okay, so what do I mean by a bimodule? So if A is an abstract spin system, I'll just call it abstract OO. Abstract spin system. I'll put these dots so I don't get in trouble. I haven't had that issue before. A is an abstract spin system. then a DHR bimodule. So let me just say, a DHR bimodule is so the real definition is kind of technical to define what I mean by bimodule. It's like a unitary version of what I'm about to write down. So I'm going to write down an algebraic version, which is not wrong, but the real version you want is like a unitary version of what I'm about to write down. So is an AA bimodule. So this is AA bimod. Okay, so it's a vector space. It has an action of the big infinite dimensional algebra on the left and on the right. Okay, that's so far not bad. So it's an AA bimod.
Finite dimensional?
No, definitely not finite dimensional. Such that, let me come over here. Sorry for this shoddy board work. Such that there exists an R so that for any interval of size at least R, so okay, I'm going to give you the definition for in 1D, but this makes sense in higher D. For any interval I with I bigger than or equal to R, there exists a projective basis. A basis BI such that x BI equals BIX for all x in A sub I complement. So A sub I complement is the subalgebra of A generated by operators supported in the complement of the interval. Okay? So what I'm saying is that I have a bimodule, and for any algebra or for any interval that's sufficiently large, I can go in that bimodule and find a projective A basis. So I'll tell you maybe if you're not familiar with that term what that means in a second. Such that for all the operators localized outside that interval, they commute with this projective basis, right? This is a bimodule, so there's a left x action and a right x action, and it's asked that they agree on these basis elements. What is a projective basis? So it is not a basis, right? These things are infinite dimensional, so you're not going to have a nice finite basis. It's a projective basis. So what I mean by that, a projective module is a sum end of a free module. And so whenever you have a sum end of a free module, you can take the image of the kind of trivial ones in there and look at the image under the projection down to it, and those will be a projective basis. So there's a more formal abstract definition, but I don't want to go too far into it. But the point is, this whole module is kind of generated as a right module by these BIs, and I can have these BIs kind of be localized in any of these intervals in the sense that for operators localized outside of them, they commute. Yes?
To be clear, X is defined abstractly.
Yeah, it's an abstract bimodule.
I'm looking some kind of locality condition.
On the object, yeah. So I'm taking an abstract bimodule, that satisfies this property for some R. I don't care what R is. There just has to exist somewhere.
Which is some kind of locality property.
The way to think about this. So I totally this idea is a way to characterize what's called the Doppler. So DHR, I should have said, stands for Doppler, Hagen, Roberts, who were doing algebraic quantum field theory, and they study localized transportable endomorphisms. This is a generalization of a localized transportable endomorphism, and saying that there exists a BI basis in I means I can localize this in I, and then saying it's transportable is saying I can do it for any sufficiently large I. So it's like I can localize my bimodule in any interval. That's how you should think about it. Is that it's localizable, but whatever interval I want to. And so this is closely related to the DHR endomorphism category, but those definitions don't work at all in this setting, because the algebras are locally finite dimensional. Using endomorphisms is totally the wrong thing. It doesn't capture the picture at all. So you need this bimodule generalization. So I introduced this, but I was very closely following the ideas of DHR, and indeed the proof that this is a braided tensor category follows closely the original proof that the DHR bimodules form a braided tensor category with some additional subtleties. So for those of you in the know, and I think Arthur already mentioned this about Hog duality, to prove the theorem in the DHR setting, you need this really strong condition called Hog duality. And you need something here, but it's actually much weaker. It's called weak algebraic Hog duality. And I'll just tell you what that means really quickly. Weak algebraic Hog duality. What is this? It's this. So there exists an R such that for all intervals I with the size of I bigger than or equal to R, let me say there's an R in S. So that if I take the commutant, so let's see, I want to get this right. So I take all the stuff that commutes with the complement algebra. So I look at all the operators in A that commute with the stuff in the complement of I. Certainly this will contain AI, because AI commutes with everything that AI complements, but I want this to actually be contained in, I want it to not be too far away from I. So this is just if I take I and add on S to I, like add on S to both sides. That's what I mean by this I plus S. It's not a translation of I, it's expanding of I by S. So this says for any sufficiently large interval, if I look at the operators that are localized outside that interval and say what are the whole operators in my quasi-local algebra that commute with it, it's pretty close to being AI. It's not necessarily AI on the nose, but it's contained in a region that's not too much bigger than the I algebra. And in the strong version of Hog duality would just say this equals AI. Okay, that would be kind of the strong thing. And then in AQFT, it's even stronger because everything's on a Hilbert space, and you need to take the relative not the relative commutant, but the commutant in the whole B of H. So that's an even stronger condition. So this is much weaker than the usual versions of Hog duality, and it's algebraic because I'm just working inside this algebra. There's no Hilbert spaces. It's about relative commutants. But you need to assume this condition is true, and then the DHR proof, essentially, the idea of the DHR proof works great. And so that's what this condition WAHD is.
Can you repeat what the prime was?
Yeah, so this maybe is unfamiliar notation. Let me just write this as the set of X in A such that X commutator A sub I C is 0. So it commutes with all the operators localized in the complement of the interval. And all fusion spin chains satisfy this. So all those examples we were caring about these ACX, satisfy this. So there is a DHR braided category. And okay, so coming back to this DHR category, the objects are these things. The morphisms are just intertwiners of bimodules, and the tensor product is just the relative tensor product of bimodules. It's just like, if you have bimodules of an algebra, you can take the relative tensor product. That's what the tensor product is. The whole game is building the braiding. And you use this localization to essentially say, okay, if I have two of these bimodules, I take their tensor product. Then I pick bases that are localized far away from each other. I swap the bases. And then I pick bases that I use a unitary to bring them back to each other. And you just check that it works. It satisfies the braiding. And you need this condition to get everything being well-defined and show that's not too far away from each other and you have a good braiding.
Why is it braided on a 1D chain?
Yeah, because, yeah, that's right. So you should think there's secretly a time direction that's happening here. The whole, having the algebra, when you're applying the operators, you're moving out in time. And so the bimodule is going out in time. But it's exactly because I have disjoint intervals. I have, when you have bases, these kind of projected bases localized in disjoint intervals, I take the relative tensor product and I swap them. That actually gives you a well-defined bimodule intertwiner. So it doesn't work in 0D because you don't have disjoint regions. Like everything's localized at a point. So that's why it doesn't work in 0D, but it works in 1D. And the point is there's secretly a time dimension going on here. That's where whenever you have operators, you can compose operators, and things are actually happening in that direction. That's why, you know, the usual topological picture actually is applying here. Okay, good. So let's see. So is there anything else I wanted to say about these things? Yeah, and so the idea, let me just like briefly say, QCAs are a special kind of automorphism of abstract spin chains that take algebras localized in I to algebras localized in I sub I plus R. Like they don't move operators around too far. And these are an interesting class of discrete time dynamics. They're related to all kinds of important things that I was going to tell you about, but I won't. I'm out of time, so I won't tell you about. And we want to study them. We want to classify them up to finite depth circuits, and I was going to tell you about all kinds of results there. But one of the ways you can classify them is that if you have a QCA, it actually gives you a braided autoequivalence of the DHR category. So when you have a homomorphism from QCA to the group of braided autoequivalences of the DHR category, and in the fusion spin chain case, it's the Drinfeld center. And so you have this kind of topological index. And relating to like Margarita's talk yesterday, you can take, you know, for these flow K codes, they give you boundary QCAs on the boundary algebra, and then you have this topological index, and that kind of captures how the dynamic automorphism codes are acting on the bulk symmetry. So anyway, there's all kinds of connections, but I'll just stop here, and we can do questions.